Hello students, in this video we'll discuss closed subsets of the real line with respect to the metric topology. We say that a point A in R is a limit point of a set F if every neighborhood of this point A meets F in a point other than A itself. What does that mean? Equivalently, for every epsilon greater than 0, this means for every epsilon greater than 0, we can look at this set, the intersection of the point A minus epsilon to A plus epsilon, intersect the set F, excluding A if A happened to be in F, is not empty. Okay, that's the condition that means for it to be a limit point, right? And so now let's prove a little proposition about limit points. So here's a proposition about limit points. And what we're going to do is we're going to use this notation for limit points. Notation, F prime is the set of limit points of F. This is the limit points of F. Okay, so here's our proposition. So A is a limit point of F if and only if there's a sequence an with a condition that none of the terms in the sequence are equal to A themselves, and these points A and are in F, and AN converges to A. Okay. So let's prove one direction of this. Let's prove the first direction. So proof. Let's assume that we have a limit point. Assume A is a limit point. Okay. And then for any n in n, for any n in n, I know that A minus 1 over n to A plus 1 over n intersect F, not A, is not empty. Okay? And so what I can do then is I can choose, I can pick select AN to be points, a point in F, and A minus 1 over n to A plus 1 over n. I know I can do this because that set is not empty, and that point will not necessarily be A. So this point is AN, not equal to A, and it's in this set over here. Okay? And so now what do we know? I claim that, so I have the condition that these points are in F. So my point ANs are in F. That's good. That's what we need. They're not equal to A. I just need to show that this sequence converges, the sequence I've constructed converges to A. Well, that's easy to see, right? If I let epsilon be greater than 0, we pick n capital in n such that 1 over n capital is less than epsilon, and we let little n be bigger than or equal to n capital, right? And then what can I say the difference between an minus A? Well, what do I know? I know that this is in an interval of length 1 over n, right, over here. So in other words, this is going to be what? I should probably put a 2 over epsilon. I'm going to probably give a vector of 2 over here. But this interval has length of 2 over n, right? So the absolute largest these can be is going to be what? It's going to be, that's going to be less than 2 over n, which is less than 2 over n capital. And then, of course, I could probably say n capital less than epsilon over 2 to make this a little bit nicer over here. So I can put a If we can change this 1 to a 2, that doesn't change my Archimedean principle, and that will give us exactly 1 over here. Then that's going to be less than epsilon. Okay, so that's the first direction over here. And let's do the second direction over here. The second direction is equally easy, right? Let's assume that there exists a sequence an not equal to a. The an are in F, and an converges to a. Let's assume this. I want to show that a is a limit point of F. Okay, and so what we want to do is we want to show that any interval of length epsilon is going to meet that. Okay, so since this is true, let epsilon be greater than 0, and then choose n, select n capital in n, such that what? Such that if n is bigger than or equal to n capital, we have what? We'll have that an minus a is less than epsilon. Okay? And so, of course, what does this say over here? This says that what do we know about these points an? These points an are in F. And what do I know? I know that an is in F, and it's in an interval of centered at a of radius epsilon. So the interval, therefore, if I go from a minus epsilon to a plus epsilon, this will contain the number an, and an is itself a member of F. That's a member of F. And so in other words, the intersection an minus epsilon, so a minus epsilon to a plus epsilon intersect F minus the point a itself is not empty since an is in there, and that says that a is a limit point of F. So it says that a is a limit point of F, and we have our result. Now we're in a position to define what it means to be a closed set, so we say, definition, F, a subset of R, is closed if and only if F prime is contained in F. Namely, F contains all its limit points. F contains all its limit points. And that's the definition of a closed subset of R with respect to the metric topology. And we're going to use this sequential characterization of limit points frequently in our analysis of closed sets. Thank you very much.